So let S be a subring of a commutative ring R. A polynomial with coefficients in S is said to be reducible over R if F can be written as the product of two polynomials in R, where the degree of G is less than the degree of F. So in other words, F can be factored into two smaller terms. And if this is not possible, if F cannot be factored into two smaller terms, then F is irreducible. Let's see some examples. X squared plus 1 is irreducible over the reals. You cannot factor x squared plus 1 into two smaller polynomials where all the coefficients are real. But it is reducible over the complex, because I can write x squared plus 1 as x plus I times x minus I, factoring it into smaller polynomials that use elements in the complex. Okay, let's do another example. X to the fourth plus 1 is reducible over the field Z5, because I could write x to the fourth plus 1 as the product of two smaller polynomials with coefficients in Z5, the operation mod 5. So I could do this as x squared plus 2 times x squared plus 3. If you multiply this out, expanding terms, working mod 5, I think you will get x to the fourth plus 1. Let's do another example. X cubed plus 3x plus 2, this is irreducible over Z5. Why is that? How do I know for a fact that I cannot factor this polynomial into two smaller polynomials with coefficients in Z5? Well, suppose I could. Suppose I could factor this, so I could have x cubed plus 3x plus 2. If I have a degree 3 polynomial and it's reducible, then that means one of my factors has to be degree 1. It'd have to look like x minus alpha times x squared plus ax plus b. And maybe you could even factor this third degree polynomial into 3 linear terms, but at least I know I have one linear term. This means I have a root in Z5. So if I could reduce this polynomial, since it's degree 3, I'd have to have a root in Z5, but I don't have a root in Z5. I could simply, let's call this f, I could simply evaluate f at each value in Z5. There's only 5 numbers. I could plug them all in and see that none of them equal 0. So f of 0 is 2, f of 1 is 1, f of 2 is 1, so you plug in 2 here and then work mod 5. F of 3 is equal to 3, and f of 4 is also equal to 3. So I never got 0. That means I can't factor into a linear and a quadratic term. So that's why this polynomial is irreducible. It's actually easy if you're in z mod p to see if you have a 0. You just check every one of the p values. So here's another example of the same phenomenon. X cubed minus x squared plus x plus 2 is irreducible over z 1,000,003. One million and three happens to be a prime number, and I wanted to see if this degree 3 polynomial was irreducible. So I simply checked all values of this function between 0 and 1,000,002 on the computer. So I wrote a little computer program just to do each one of these values mod 1,000,003, and none of them got 0. So that's irreducible. Okay, let's end this video with another definition. So here's a definition. A polynomial let's write it as an x to the n all the way down to a0. And I'm going to say for this definition, my polynomial has integer coefficients. So this is primitive. It's a primitive polynomial if the greatest common divisor of all these coefficients is equal to 1. So let's do an example of a primitive polynomial. 3x squared plus 12x plus 4 is primitive. The integers 3, 12, and 4 have no common divisor except 1. So the greatest common divisor of 3, 12, and 4 is 1. It's primitive. The polynomial 6x squared plus 12x plus 4 is not primitive. The greatest common divisor of the coefficients is 2. If you have a polynomial that's not primitive, what you can do is factor out the greatest common divisor. So this polynomial, I could factor out a 2, and I guess I get 3x squared plus 6x plus 2. And now this is primitive. So in the next video, we'll prove a theorem about primitive polynomials due to Gauss. All right, see you there.